Hello guys, this is the fastest revision video of process control. So this is meant for revision purpose. So let's start. Please just like, share, subscribe, whatever you want to do with the video. Let's start. So first thing is the various input functions that we need to see. First is like step function. So step function is like this, or everyone knows. So let's take the magnitude as 1. So then in time domain it is actually 1. Okay, that's because of this step 1. So in S domain it is the Laplace domain, it is 1 upon S. Laplace of something f of t is nothing but integration of 0 to infinity e of minus st into f of t dt. Okay, so 1, the Laplace of t raised to power n is actually n factorial by s to the power n plus 1. So 1, so if it's t raised to power 0, that is 1. So 0 factorial is 1 and s raised to power 0 plus 1 is s. So 1 upon s. Now the next thing is the ramp function. So before that, also if there is a first order system, let's say kp, and x of s coming in, y of s going out, then we know that this y of s, and if this is a step function, then what we need to know that y of t is kp 1 minus e to the power minus t by tau. Okay, so now here this y of t is actually y of some time t minus y at steady state. Okay, this is the difference between the two. So the next thing is the pulse function. So what is pulse function? Pulse function is like one step up, then another step down. So plus 1 magnitude and then minus 1 of magnitude at, let's say, 0 times 0 and let's say some time a, t is equal to a. So it would be in S domain, it would become plus 1 of S. Why? Because this is one of the step and then the down of the step. Minus 1 into step into e to the power minus at. Okay, this we will see how it is. So basically there is some theorem of the Laplace, that Laplace of f of, so f of t minus a, so Laplace of f of t minus a is nothing but e raised to power, because it is in t minus a. Okay, so minus is there, so what we will do is minus as into f of s, where this f of s is actually Laplace of f of t. Okay, if there is some difference in the time t minus a, in that case you can just remember that e raised to a minus as is to be multiplied with f of s. F of s is Laplace of f of t. And one another thing is, if the Laplace inverse of f of s minus a, now this is in s thing and minus 1, if there is a function, so we need to take the inverse. For s minus a, it is a raised to power plus as. So s minus a, then this becomes plus. For s it becomes plus, for t it becomes minus, because you can remember that t is like this, so there is this, so t minus. Okay, anyways, for s this and for t that, so e raised to power plus as into f of t, where this f of t is Laplace inverse of f of s. Okay, now the next thing is, one also important Laplace rule is that if Laplace of, let's say, t raised to power n into f of t, if you want to do this, remember this, that t raised to power n, so minus 1 raised to power n into prime into f prime, not this, into f prime s, f of s, and then differentiate it. Okay, this is one of the most important Laplace rules. Now the next thing here is, we have discussed pulse, and what was pulse was 1 minus e raised to 1 by s, e raised to minus as upon s. Okay, that was for pulse. Now for ramp function. Okay, now a ramp function is simple, it is continuously increasing, okay, like this. And so it is in t domain, it is at, a is some magnitude of that increase, and in s domain we can write it as a upon s square. Now what will be y of t? Y of t would be at, okay, y of t would be at minus a tau into 1 minus e raised to power minus t by tau. This is simple to remember, this is same as the step. This is a tau and here it is a t. Okay, a t and here it is a tau. Remember this. So these are of the same quantity, and this is a function of time, this is a function of time. This is way you can remember this. Next is my sine. So sinusoidal function, which is like x of t is a sine omega t. One important relation to remember here is this one, that y of t that comes finally is this thing for first order system, 1 minus omega t whole square. Okay, this is the magnitude into sine omega t plus phi. Phi is this the phase lag, the phase difference here. Okay, so next thing is the final value theorem. Final value theorem means final value means when t tends to infinity. Okay, that then we will get the final value. So this theorem states that when f of t tends to infinity, if t tends to infinity, this theorem says that take limit t tends to infinity, so s tends to 0. Okay, these are just the opposite into s. Okay, into s into f of s. F of s is mostly here like y of s mostly. Okay, this is final value theorem. And the next is initial value theorem. Initial means t raised to power 0, tending to 0, or t is equal to 0, t tending to 0. So if when t is 0, t raised to is equal to 0, so f of t, we want to find out the initial value, then we will take limit in s domain here, s tends to infinity, and again the same thing, f into s into f of s. Now the next thing is that boundness. What all functions are called bound? So boundness here means that if, let's say, my ramp is unbound because at t tending to infinity, it is continuously increasing, it is not getting some constant value. Like a step function, it finally attains, after one step, finally attains a constant thing. It is not just increasing with thing, but this ramp is increasing. So this boundness means at t is equal to infinity, it has some finite value, then only it is bound. Next thing is the let's take the step function, which is one of the important functions only. So let's say my step response, it mostly comes like this. Okay, it goes and like this. This is mostly my step response, where we need to see that around 63.2%. Okay, 0.632 into kp. Okay, 0.632 into kp, let me write it better. So 0.632 into kp times, so around 63.2% of the maximum value, that's kp, is reached at time constant tau p. Okay, and now if we want to find, in some cases we want to find the initial slope. Okay, so initial slope would be like this. At 0, what will be the initial slope? It will be like this. So here it will touch this kp point. Okay, so initial slope, this is delta y upon delta x, which means this initial slope is kp. Okay, kp upon kp minus 0, so kp upon tau p. Okay, and if there is some magnitude of the step function, then a would come here. Okay, this is my initial slope formula. Next thing is one important thing, how would you see which system is faster? Okay, so to see which system is faster, so if the time constant of the system is less, then this means this is faster. Next, for first order system, the general equation is like this: tau p dy upon dt. Okay, this plus y is equal to kp x, and this is also function of t, this is function of t. So what we do when we take the Laplace, okay, d by dt, the Laplace of the dy by dt is s into the Laplace of y. The Laplace of y means y of s. Okay, minus when y was at t is equal to 0. Okay, this is Laplace. So let's say y at t is equal to 0 is actually 0, so s into ys. This becomes, okay, so this becomes s into y of s minus y of s is equal to kp x of s. Okay, if we take this common, so this becomes tau p s. So if this is plus, actually tau p s plus 1 into ys is equal to kp s. So finally ys upon this is kp upon tau p s plus 1, which is the first order thing that we know, the transfer function. Transfer function is y of s kp tau p s plus 1. Okay, this is the thing. Now this tau p, depending on the various the systems, it is changed. So let's say take the tank system. So for tank, this tau p is ar. What is a, what is r? So this is Like, let me write it. So let me first draw the tank. This is my tank. Some qi is coming and qo is out, and this height will actually change. So this is my height of the tank, and this will change according to this qi. Also this q naught will change according to this qi, because qi is my disturbance here. Okay, so what we do is we first take up general case that q naught is h by r. Okay, where r is that the resistance here. There is some resistance here also. This resistance is r. Okay, we take this r, and so what we can do the balance is in minus out is equal to the volume. So this is volume per meter, so this will become d of volume by dt, but area is constant, so we can take area out into h. So this is the thing. Q naught here, let's say for linear h by r, so this way we can finally get ar as r, a into r, this goes there, so tau p. Now what happens if q naught is not h by r? Okay, well, if let's say q naught is let's say h square, so how would you find this r? Okay, where is r here? R is not here, but then you can find an equivalent r by this very special equation. R is equal to 1 upon divided 1 divided by the f of f naught, q naught. Okay, this q naught is a function of like h, but we will put hss and we will take the derivative of this. What really means that, let's see, my q naught is h square. Okay, my q naught is h square. So what I will do, I will first take the derivative, that is 2h, and I will put hss. So 2hss, this would become, and my r would be 1 divided by derivative of this, so 2hss. This would be my r. And how to find this hss? Height at steady state. So height at steady state, we can find out when it is the steady state, when this height is constant. And how it will be constant? Whatever it is coming, it is going out, no accumulation. That means qi and qo should be same. This means my steady state. Next thing is purely capacitive system. Purely capacitive system. What does this mean? This means that here what will happen, like I have written dy by dt plus y is equal to what was that, kp into x. Okay, this is okay, but what will happen if my y, this is 0? So then what will happen if we take the Laplace of tps? Now there is no plus 1 into y of s is equal to kpx. So what will happen? Purely capacitive system, there this y of s, or capital Y, the transfer function would be in this form, kp. It would mean kp by tau p s, or we can take this together and it would be k by s. Okay, this is the transfer function for purely capacitive. There is no other extended term. But what does this really mean? Let me show you with an example. If this is my tank only, and again the height h, and if it is going out, now I put a pump. Okay, now I put a pump, so my q naught is constant. My qi is changing, my height would also change, but my q naught is constant. So what we write is q minus q naught. Here the q naught, the change in q naught is actually 0. Why? Because q naught at steady state is also same, at normal operation it is same. So that is why this particular term becomes 0. Okay, now we move to one important thing is for thermometer also. So let's say with thermometer, just remember this tau. Okay, tau is mcp upon h. Okay, we just need to remember this tau and just put it in the equations, in the first order equation, and you will get for everything. So now next thing is, one more important thing is proportional band. Proportional band. Let's say this is my band of measurement. Okay, so this is my band of measurement, and ideally it is more. This is my ideal. Now I take, but I just need only a particular part to measure. Out of this whole, I just need only particular part. So this is my actual. How much part of the ideal you take the actual measurement? This is proportional band, so I will write PB is equal to delta actual by delta ideal. That is my proportional band into 100, so you can get the percentage. Okay. Meanwhile, also remember this, that 4 to 20 ATM, no, not ATM, ampere, and 3 to 15 PSIG are some bands that we measure in the industry level. Okay, so they are industry level measurements. Now next thing is let's move to second order now, because first order is complete. So second order, just remember that the transfer function I will write TF, okay, that is KP, and this lower term is important, that is tau square S square plus 2 zeta I will explain tau S plus 1. Okay, so this term is very important because this has this damping coefficient. What does this damping coefficient mean? This means that let me make. So this is my point of my starting point when I put some deviation. It's a step deviation. So my response could go like this. My response could go like this, or my response could go like this in a second order system. Okay, so when this is zeta less than 1, this is zeta equal to 1, this is zeta greater than 1, this is critically damped, this is underdamped, this is overdamped. And similarly, let me draw it over here. Okay, this is my, let's say, Q, this peak, this is my overshoot, this from bottom it is P. So I really want to reach my P distance only, but due to the underdampedness, the oscillations are there. So this is my P, this is my aim. So this is my aim, is my ultimate value. Okay, aim is my ultimate value, but my maximum value that I can reach is P plus Q, that is this P plus Q is maximum value that I can reach. Okay, so this goes again up, okay, but with smaller peak, and this peak, let's say I denote it by R. Okay, this is only the peak. So this is P, and then a little bit up, Q, the highest peak, then a small peak because there is a decay. Okay, and slowly and gradually it will come to almost P, because that is my ultimate value, my aim. So this overshoot formula is Q by P. Okay, how much peak I attain over my aim, over the shoot, over this. Okay, so overshoot is Q by P, and this is given by, okay, so Q by P, this is given by exponential minus pi zeta by under root 1 minus zeta square. Okay, and now one another thing is how much decay ratio. Okay, this is my second peak, this is my first peak, these are how much decay is there in the peak. So decay ratio, the second peak by the first peak is just overshoot square, so Q by P whole square. Or if you say like this is exponential to the power, let's say x, so if e raised to power x whole square, then it is e raised to power 2x. That means we can multiply here too, and that would be my this decay ratio. Now what is that omega and time constant? So let's take this my tau square S square. Why will be there some omega and time period? Because there is oscillation. So t square S square plus 2 zeta tau S plus 1. This is my characteristic equation for this second order system. Now if I want to find this S, because ultimately this is a square quadratic, so if I want to find this S, you can do that d is equal to b square minus 4ac, and again the same thing like solving the quadratic. So you will get S is equal to minus zeta by tau plus minus, okay, under root 1 minus zeta square by tau, and this would come with iota. Okay, so if my system is critically damped, that is my zeta is 1, so this will become 0, so I will get real roots, but they will equal roots. If I get overdamped, then this would become okay, then you can put the zeta more than 1, and if it is underdamped, then you can put zeta less than 1. Okay, this thing you can do. So for this thing we have 3 important things to know. Okay, that zeta greater than 1, this means overdamped, that means there will be sluggishness, while zeta less than 1, there will be oscillations, so this would be oscillatory. Okay, sluggish and oscillatory, while all of these are bounded. Okay, that you can check at time is equal to infinite, is there some finite value, you can put finite value theorem there. So omega that we see here, so this S I have written, and the imaginary part was this. So this thing is my omega, 1 minus zeta square by tau. This thing is my omega. If you forget what was the formula of omega, just solve the quadratic, and the term that is here with this iota is my omega. Obviously plus, because omega cannot be negative. And the time period is 2 pi by omega, so it will be 2 pi into tau under root 1 minus zeta. This is my time period of oscillation, while my time period of the whole system, natural time period, would be tau p. Okay, so these were the things here. And next, let's say two systems are like this, two tanks are like this, coming in, coming out. These are also second order examples. So if this comes out like this, then this is non-interacting, okay, where because this height, the height here won't actually affect this. So what we can see, the transfer function we can write as the product of, let's say this is transfer function 1, transfer function 2. So transfer function 1 into transfer function 2. Okay, we can write the product. What I mean here is, let me write. So that could be means like q, let's say this was qi, then after that q1, then q naught final. This is qi and this is q naught final. Okay, so you can write q. So what will happen? Q naught by qi, this would be equal to q1 by qi into q naught by q1. So this will cancel out. That's why we do the product. Okay, there is everything here. There is a reason for that. And this would be finally like 1 upon, okay, tau 1s plus 1 into tau 2s plus 1. This is for non-interacting. But what will happen if it is interacting? So interacting is like this. Okay, this goes directly into this tank. So this height and that height. Okay, this is q naught again. This is qi. This is q1. And also there are some resistance, and we know that tau is equal to AR. So you can find out, but I will write it tau only here. Okay, tau is AR, that you know. So there's some resistance also here, R2, here R1. So here this height 1 and height 2, if this height 2 will actually try to move here also and here also, like this, the gravity will actually force this back, while it will also force this to move out in both directions. So this height will actually influence this height. So what we finally get for interacting system, the transfer function is this case. Like it is, if we say for h by q, so h2 by qi. So one thing, remember that the transfer function of q naught upon qi is 1 upon tau s plus 1, while for h by qi it is r upon tau s plus 1. Why? Because my q naught is h by r. If I am taking this, then only it's valid. So what will happen? Q naught, so h would be q naught s into r. So r will be multiplied with this r we are multiplying. Okay, so what we see here is that the transfer function finally would become like this. It would become r2. Okay, the second height. Okay, the second tank's height, resistance, sorry, r2. Why? Because we have taken, it's like this. Okay, we have taken the height of 2 second. That's why r2 is coming at the top. And this I'm writing the final expression here. Tau 1 into tau 2 into s plus tau 1 plus tau 2 plus, now one trick to remember is r2 is above, so write r2. But if we write a2, then this would become tau 2. So we will write a1 here, a1, and into s, this whole thing into s plus 1. Okay, let me write it like this: tau 1 tau 2 s square plus tau 1 plus tau 2 plus a1 r2 s plus 1. Okay, this is like this. Now the next thing is so both of these interacting systems are actually overdamped. Okay, why? Because they have a sluggishness. Because this is coming like this, why not take only one system? Then it had been less order, so that would make it more faster. Okay, so these are overdamped, so they are slow actually, these both tanks and systems. Now the main thing here is what will happen if zeta is 0. When zeta is 0, then what will happen is this peak will attain, but then it will again attain the same peak. So the decay ratio here would be 1. Why? Because there is no decay actually. Let me see. So decay ratio, that is r by q, these both are same, so it will become 1 in this case. And you can even put this like 2 pi zeta upon 1 minus zeta. This is exponential. There's minus sign also. So zeta is 0. So this is 0, this is 0. So this is e raised to power 0 is 1. Okay, so decay ratio is 1. When this and the same peak would be there, so it is oscillatory. Okay, next thing is we take the servo control. Okay, servo and regulatory. In servo, remember that this YSP would is change, YSP change, and D not change. Okay, what is YSP, what is D? Simple. Let me put it. This is my, let's say, okay, let me erase it, make it better. So what is YSP? What is this? Let me just erase it. Okay, so this is my suppose set point. Okay, YSP is my set point, and this goes with some into the system here for a feedback. This is my GC, this is my GP, and there is some disturbance also with, let's say, GD, disturbance in the system, and my Y is outlet, and this goes up and goes back. This is my, let's say I'm putting some measuring device, so GM also, plus minus, plus plus. So this YSP, if my YSP is changing, because I have three things, YSP, D and Y. So if my YSP is changing, then this is servo, but in servo D is 0. Okay, in servo D is 0, while if my YSP is 0 but my D is changing, then this is regulatory, in which the D will change, that is regulatory. So if one is non-zero, then the other one is 0, that is, if this is changing, then this is non-zero, so this is servo. So in servo D is 0, in regulatory YSP is 0. Simple. And what is offset? Offset we need to know. Offset is, okay, offset is this Y of SP, okay, the set point, the final value of this, that's like infinity, minus the out of final value. So the final set point change minus the final change in the out. So the change, the final change in minus the final change in the out at infinity. Okay, how to find this? Obviously at infinity means we need to use final value theorem. Okay, but first let's understand for servo. So for servo, the transfer function, that is Y upon YSP, or these are the differences. Okay, y here I've told you it is Y of t minus Y of at steady state SS. Okay, remember this because this is important. Some people make mistakes here. Okay, so Y of this. So first, in that particular loop, the transfer functions between, so this was like this. So the transfer functions between YSP and Y, they are above, so write them above. Okay, it could be like GC and GP only. I've taken this. If there is some another transfer function here, GSP, then we'll write GSP also here. Okay, so this is the thing between these two. Whatever the transfer function at the top, we will write at the top. Then at the bottom, we will take the open loop transfer function. And remember this thing, that this is coming, this is now this thing. Okay, this is my YSP. If this is plus and minus, if this is minus, then this is plus. Okay, at the bottom. And the open loop transfer function is, we will first just make this loop like this, open loop. We'll open this up, and we see that this goes up like here. So this loop, so C, GP and GM, these are in the loop here, and we will write them down. So that is 1 plus GC GP GM. M is for measurement. This is the thing. Why I've not taken D, because this is servo, so YSP. Okay, so this is for that. You can take final value theorem and find out the offset, that is YSP infinity. But now regulatory is important. In regulatory, D is not 0. That means we will have GD and the Y prime by D, because now D will come because YSP is 0. So this would become GD. Okay, why GD? Because this goes like this. If you remember this whole thing, okay, if you remember this whole thing, this goes like this. So only GD is here between the D and Y. Okay, so we write GD above, and 1 plus same thing. Same thing means the open loop transfer function plus 1. Okay, this is the thing. But remember, in regulatory response, one thing very important, that offset is equal to always Y SP infinity minus Y of infinity. This time the Y of SP of infinity, there is no change, so Y is changed, but set point is not changing, only D is changing. So this will become 0, so it will be minus of, so 0 minus Y of infinity. Remember this in regulatory systems. Next thing is there are some exceptions that you need to know. One is like this is Kc. Kc, like say I have, for first of all let me see the controllers. So controllers, I have proportional controller, that means the output, or let's say I will see the output, let's C or Y is Kc times of error, and there is Pi. Okay, Y is Kc times of the proportional plus the integration. So integral of error dt. Okay, so this is proportional plus the integration. Okay, and Pd, this is the proportional. Okay, this is error, proportional plus the differentiation. Okay, simple. But here you need to remember that when they are used. Okay, but that let me just tell you, p is used when there is proportionally you want to fix the error. Okay, but there is always some offset here, and this offset is actually sometimes, if it is tolerable, then only we can do this. But if this offset is let me just tell you that is Y is equal to Kc error, so there will be always some offset, because some error, if there is some error, it would just maximize this. Okay, if Kc is my high, it will just maximize this, so difference will be more. What will be happen, that if Kc tends to infinity, that if Kc is very large, okay, so my error would actually, like, it would be really small. In that case, what will happen, it will be working as an on and off. Okay, so let's say I put some increment here and my Kc is very large, infinity. So just some difference would multiply this and make it too large, that it is either on or it is off. Okay, when Kc is in almost infinite or very large. So now to remove the offset, we use Pi, and here I, what it does, let's say this is my loop. Okay, this goes and there is some error that GC takes into account. Error is here. Error means YSP minus this Y. Let's say GM is 1. This is 1. So error is actually YSP minus Y. So there is some error in the first time. In the first response, one time run, there is some error 1. In the next time run, okay, again we will run this. YSP is changing, or it has changed. So if we are fixing, we are trying to achieve this Y. So there is some error. There is again the run. There is some error. What will happen? Integral will integrate all this error and take into account. Okay, so it will integrate this error, and the past error will be there. So the past is also there. Just this thing you need to remember. Okay, and in PD, so in D derivative, PD, it's what? First it will differentiate the error. Okay, some delta error. Then with this error, the present and the future will be determined. Future, what value of error could come. Okay, so this PD will determine the future. No need to just think that way, but these are some concepts that I'm telling you, so that you don't finally find them difficult to understand. PD, Pi, and this. So mostly for level measurements, or level flow level thing is the proportional. For let's say P and I is used for flow, and PID, all of the three are usually flow from temperature and pressure. Level Y, because how much it is changing, it will change accordingly, that level. Okay, that's what level is. Okay, now the next thing is we move to route array. So what is route array? Route array is you had this characteristic equation that is at the bottom. Okay, in the denominator, this characteristic equation, we just need to take this, that is 1 plus the open loop transfer function. That means like 1 plus we did that GM GC GP GM. So this thing can actually tell us the stability, tell us about the stability. So this would be like a polynomial if you solve this, because let's say GM is like S or something, okay, tau S plus 1. In that case, when you open this will become a polynomial, and the polynomial should have be like this. So we can, I'm writing this A1 A2, these are the coefficients of the polynomial. This could be anything by solving the polynomial. So these are like A0, this is like A0 S. Okay, it depends on which type of polynomial, but let's say for example it is like quadratic. Okay, so a naught s square plus a1s plus a2 is equal to, let's say, 1, or some plus is equal to 0. Let's say this kind of equation comes up. This is my polynomial, or yes, this is my polynomial. This could be also third order, fourth order, but let's take this, and it could be anything. One thing first to check the stability is that make this positive, then all of these should be positive. This could be kp also, okay, not 1, kp or something. So all of this positive, all should be here positive. Then we need to look further. If one of them, if this is positive, then this is negative. Let's say this is my positive, this is negative, then this is unstable. So signs should be same, or in fact make this positive, so everything should be positive, else unstable. Now what we need to do is that, let's say we have 5. Okay, let's take 5 1 a naught s raised to power 4 plus a1 s 3 plus a2 s, let's say 5 2 a1 s 1 plus a1 2 3 and a4. So let's say 5. So 5 4 3 2 1 and no, and a into s raised to power 1 plus a5. Let's say this kind of thing is there. Okay, so what we do, we make the route array like this. Okay, put a first, a naught, then go here, then here, then here, then here. Okay, this way, make a w, a1, then a2, a3, a4, and a5. Okay, I'm taking a 5th order because that will also consist of the 3rd order, if because you can simplify that for the 3rd order. If this is 3rd order, so a naught, a1, a2 would be there. In that case, you can remove this will be 0. Okay, that you can do. So first you need to do is find the lower things, that is b1, b2. Then how to find this, that the formula is for this b1, 1 is like a determinant but the opposite determinant. This multiply this and minus of, then minus of this multiplication. So thing is, b1 is a1 a2 minus a naught a3 by a1. Again b2 is a1 into a4 that side, and then a naught into a5 upon a1. Okay, this thing. And again, if for finding the c, you can like it was a naught 1 a naught a naught 1 a2 a3 a4 a5. So finding the c, like this is what was b1 b2 is would be c1 c2. So finding c. Now do this like this. This is 0. Okay, this comes as 0. Okay, so this way the route array would be built. And now if say my route array is like this, a naught a1 a2 a3 a4 a5 b1 b2 c1 c2, and this goes on, let's say d1 e1. So if this is my whole route array, then we need to see that how many signs are changing. If b1 is, let's say, negative, this becomes negative. So how many signs change? One sign change. Let's say this is not negative. One sign change, then two signs change. So this will give me how many imaginary roots are there. Okay, the number of sign changes. How many real roots would be there for this sign change. And what we have is the last columns, that is c1 c2 d1 and e1. Let's say e1 is 0 or something, is the 0, let's say, the last thing. Then this thing, this d1 would be the route element. Okay, e1 is also there, so one above this would be my route element. Okay, and my system would be marginally stable. My system would be marginally stable when we will have imaginary roots when p s square plus q is equal to 0. This is how we can find the imaginary roots. And to find this one, p is actually c1 and this q is c2. Okay, above the route element was d1. Above the route element, this is the thing. Okay, and before that, okay, route element, this is like d1, so this would be 0. Okay, And next thing is, okay, so this was the thing. And for dead time, let's move on to next topic. Dead time. Dead time is like there's some pipe, so TD. So I'm entering at x, let's say at 0 time 0, but it is coming out at some time TD. So there is some time difference. So what will happen? We will put, so my out would be, out y, okay, of t would be x of t minus td, because there is some time difference. Let's say I'm giving at giving at some time, but the out is coming at 4 time, while inside it has spent 3 time. So actually I gave 1 time, okay, like 1 then 4, so my final time would be 4, but actually my t here, that is my 4, but actually my x I'm putting at this time. So just remember this, that t minus td is done because this time is extra to what I have actually changed here, and the change is finally obtained after this time. That's why x minus td. Then this y of s would be, again it's e raised to a minus s into td into x of s. So if x of s goes down here, then this is my transfer function, it is e raised to a minus std. td is my dead time. Now we have Bode plots. So for Bode plots, these are like this. So let me take, for Bode plots, what we do is we change this s by omega iota. Change for frequency analysis with this, change this s with omega iota for frequency analysis, and you will get finally the amplitude ratio for first order system would be kp upon under root 1 plus omega tau p whole square. This would be the amplitude ratio, and this would actually, like for first order system, so my Bode plot is like this, first like this, okay, then there's a curve like this and it goes down, but this we can take the asymptotes, and at this point this is my corner frequency, and because this is my corner point, so this is my corner frequency, let's say omega c, and this is my 1, okay. These are ln plots, okay. And here at the this side y axis we have my mr, okay. So this mr, magnitude ratio, is my amplitude ratio. I've told you that formula earlier, divided by kp, okay. So amplitude ratio by kp, ar by kp, we knew that this is 1 upon 1 plus omega tau whole square. So what are the different Bode plots for different systems? I've talked about that, and also this important thing is phi, the phase lag difference, what you can say is tan inverse of minus omega tau p. Remember, this is minus omega tau p for first order systems, minus omega tau p. Then we have my also like this was ln point plots for dead time. For dead time systems, it is straight. Why straight? Let me just show you also how these are actually obtained. The quick thing that we knew e raised to a minus std, okay. So the amplitude here, e raised to a minus something, if we put that in, okay, so what you need to do is e raised to a minus std, we change this s by omega iota, this will be e raised to a minus omega td into some iota, and if we use Euler's, it would be cos of omega td minus iota sine of omega td, and this is my polar form. The amplitude is 1, that's why the amplitude is 1, okay. That's why it is 1 here, and it's not changing for dead time systems. For dead time systems, if you want to find the phi, okay, I'm telling you for that so that you can apply it to any system. So for dead time system, it was e raised to a minus, or let me write it down direct, cos omega t minus sine iota is there, minus sine omega td. So if you want to find the phi phase difference, that would be tan of, so tan inverse, here what we do is, let's say this is, let's say this sine omega t and cos omega t, we do this sine omega t d and cos omega TD. This is my tan omega TD. And this thing, if we take the tan inverse of this, so my phi would actually become TD, or omega TD is omega TD. So omega TD. Why? Because this is tan inverse of this whole thing. And if you want to convert it to like degrees, because phi is in degrees, so it would be omega TD. This is in radian, so multiply by 180 by pi for degrees. We want phi in degrees. Okay. Now for purely capacitive systems, these are also important. This AR would become, although we know that this transfer function was like this, Kp or K by S square, I guess. Yes, this was like this, A by S or S square. So it was K by S. Why? Because if you just see, there was no plus term, so it was K by S. But now we will put omega instead of S, just put omega iota. So iota will go up and this will become minus. So because iota we do that. So finally we see that the amplitude will be K by omega. Amplitude ratio is K by omega. That means it depends on omega. And how it depends? If we take ln of 1 by omega is equal to minus ln omega. So this minus 1 is coming. So let me show you this. So what happened with phi we do? So phi, there was only this iota into K by S, 0 minus. And if we take this B by A, so this is my like B by A, K by S upon 0, and we see that this is infinity. So tan inverse of infinity, that is pi by 2. So this is minus also there. So that is minus pi by 2. That means for purely capacitive system, the phase difference is minus 90 degrees. So you can find this for any other system. The main important thing is to find the amplitude ratio. You need this. You need to just find this. Let's say for first order, Kp upon 1 plus, this is let's say tau p s plus 1. Put the s as omega iota. You will find some relation. Let's say A plus iota into B. So the magnitude, the amplitude ratio would be A plus A square plus B square under root. Okay. And this iota and this, so phi would be my tan inverse of B by A. These are the two simple things, and you can do it for any system and get their amplitude ratio or phi phase difference. For P action, let me list the graphs. For P action, it is this. For P action, for Pi, it is first decreasing, then straight. Okay, at corner, these are corner frequencies, and this is for Pi. Then there for PD just do this till some corner frequency and then go up. This is for PD. Okay, all of this you can just remember that two simple things. First thing is that put S is equal to iota into omega. Okay, this is first thing, and that the phi is tan inverse of B by A, where I have said A plus iota B is finally that we obtain. Now some important rules and tricks, not tricks but a way to solve that. If we find the overall amplitude ratio, we can find it by amplitude ratio of one system into amplitude ratio of second system. Let's say like I've been given K1 by, let's say, tau 1 s plus 1, this is one system, and K2 by tau 2 s plus 1. So amplitude ratio, find the amplitude ratio of this and of this and multiply this, so this will be the overall amplitude ratio. So this multiplication would be there. This is one system, so if there is a lot of systems multiplied together, you can find the amplitude ratio in that order multiplication. For phase lag, we can find the overall phase lag as phase lag 1 plus phase lag 2. This is plus, and for amplitude ratio it is multiplied. Okay, for any number of systems, if there is 3, so plus phi 3 AR 3 multiply. Okay, next thing is crossover frequency. Now what is crossover frequency? What is, so there is a gain margin. This is 1 upon amplitude ratio. Okay, and this gain margin means how stability, this defines stability. So at is equal to 1, when this would become 1 or AR is equal to 1, we can actually define some Kp here. In that AR there is some Kp. When this would become 1, or let's say AR would become 1, then we have the gain margin. We can find the gain margin at that time. Now this is my gain margin, and for my phase margin, or my phase, or you can say margin, this would occur when my phi is equal to minus 180 degree. What's my phase difference? Phase difference is that how much 180 minus phi. So that's my phase margin, how much difference between the actual phase lag by 180 minus 180 minus actual phase lag. Next, there is also, you can find the phase phi of different systems. I've told you the AR of different systems. Okay, let's say for some system, some first order system, you have tan inverse of omega tau 1, omega 1 tau 1, and you want to find the final tan inverse. You want to find the phi of final phi is, let's say two systems are there, you just add them, because I told you phi 1 plus phi 2, you add them. So use the tan inverse property. How? Let's say this is my x1, this is my x2, so tan inverse of x1 plus tan inverse of x2 is x1 x2 by this plus, so minus 1 minus x1 x2, this whole tan inverse. Put that tan over there, so tan phi, or you can find this tan inverse like this is omega, so you can get the value of omega as well. For if it is this phi is for 180, you can find omega corresponding to phi 180, you can find this omega COR crossover frequency you can get. And if you put AR is equal to 1, or let's say GM is equal to 1, that is 1 upon GM, you can put AR is equal to 1, and you can also find the crossover frequency for the gain basis. There are two crossover frequency, one for the gain basis, one for the phase margin basis. So this was a thing. Now another thing is like, so you can put that way. And next thing is what will happen if I just increase. Okay, if my AR is in greater than 1, then if AR is increasing my amplitude, so understand it this way, my amplitude is actually increasing like this. That means my system has become unstable, so my gain margin would become less than 1. Okay, in that case, so my margin is not more, but I want my margin to be more. Okay, and finally we have the different, like feed forward. We have feed forward is like this. Feed forward means some input is coming, okay, YSP, okay, let's say, or not, let's say X, okay, and there is some GSP, set point transfer function GSP. This is GSP. It comes and it goes like this till Y, and in between we have our controller GC and a process GP, but there is also some disturbance, let's say D, with the transfer function GD. Okay, so this disturbance, if we measure this disturbance beforehand, we can actually minimize this. Okay, if we measure this GM with GM, if we measure this disturbance beforehand because of this feed forward, then we don't need a feedback loop. Okay, because we have taken in account of the disturbance. So what will happen, that D is going here and it will create some disturbance, but we will take this route, measure this and control this in a way that the D coming here and D coming here will cancel each other. That is my feed forward control. How they will cancel this will cancel when GM goes here into GC into GP. Okay, this whole thing coming here and this coming here would be equal. Okay, this is a way to remember that this way GD should be equal to GM and GC GP. When they are equal, this thing will get cancelled. Okay, why? Because this is coming like here and here. So one thing is that is disturbance rejection, and the next thing is, if this thing loop GSP, then GC and GP, so if these all things are equal to 1, then my YSP, or let's say X, would be equal to Y, that I really want, because this is my set point and I want my output to be equal to set point. So this GSP into GC into GP should be equal to 1 for set point to be equal to like outside. Next thing is inverse response. Inverse response is like this. Inverse response means like, there is kp tau 1 s plus 1 minus kp2 tau 2 s plus 1. So this part will actually, this part will make it increase, but this would decrease. So we have inverse at particular tau 1. Let's say this tau 1 is, let's say, less. Okay, this is less. So first this will actually come into picture, then this would decrease it. Okay, we have a variation in the response. Okay, this is how we do. And here we need to find the zeros. Let's say this is we finally put this whole thing, multiply this, and we need to see if there are zeros in it. Okay, next thing is valve, air pressure, air to open. If this is my, let's say, valve. Okay, fluid coming, air going up, valve. So air, if my air pressure increases, air to close valve is, I'm putting air and this is closing. Okay, so this is direct acting. Why? Because I'm putting more air, and it is actually this stem, let's say from 0 to x distance, L distance, this is moving also this way. So air increase, the position also increase. So direct acting. If air to close valve, then I'm putting my air from here, from the opposite side, and this air is actually moving this and opening this. But here my distance is reducing while my air pressure is increasing. So this is air to open valve, while this one was air to close valve. Okay, air to close, direct acting. And how about direct acting, non-direct acting? If my air pressure is increasing, my position, this position is 0 to L, this position also increasing. If my air is increasing but my position is decreasing, this is indirect acting. Okay, next thing is the different valves stem position. This thing is my quick opening or square root. Okay, I will tell you this is linear, these are for valves, and this is equal percentage. What happens in quick opening? I have my flow, let's say flow is F, and this is X into F. F here, what it means is F by F max, F min. Okay, so this is F by F min, and this is X by X min. So what means? It means for quick opening, this would open very quick. Okay, what it means that F square is equal to X, or directly proportional to X. This is for quick opening. Flow increases more. For less X, let's say X is increased 1, but X is increasing by 2, but F square, my flow is quickly increasing. So guys, like, what is F and X here? But remember this graph. Okay, what is F and X here? So capital F means F of some actual F by F maximum, and this X, capital X, means X, the stem opening, this is flow, this is stem opening, by some X maximum. Okay, maximum, X maximum means the 1, and X could be some fraction of that 1. So if we do this, so we have F square is directly proportional to X. This is quick opening because flow is getting squared. Quick opening, or this would become square root if this goes. So this becomes square root. Okay, square root. In that case, that is same quick opening. If this becomes F square, that means quick opening. Okay, next is my linear, that F, this is linear, easy. Then there is my equal percentage. For equal percentage, this F is actually F min. So they have two relations. F minimum means F upon F min. Okay, this is F min, and these are dimensionless. Okay, to the power 1 minus X. Okay, we know X, and F min is F upon F. X is X upon X max. We know this X. So one is this relation for equal percentage, and one another relation is F is equal to F min. Again, F min e raised to power beta X. Okay, we can, if given depending on whatever is given, we can find this thing. Like for quick opening, what is this beta? So this is like df upon dx is equal to beta into f. So this is for my equal percentage. The derivative is beta into f. Now in question they will be given like the flow is this much for let's say x is 0.5%, 50% opening. The flow is this much for x, that is 100 or let's say 60% opening, then finds this flow. So this kind of things, this e raised to power beta, you first need to find this f min and e beta, or you can actually take like this, because f1 is equal to f min e raised to power beta x1, and if we divide it by this f min by e raised to power beta x2, so we can cancel out this out, we can find this beta and put this beta to find some f3 is equal to f min e raised to power beta x. Okay, so these were the only things that are really important for gate point of view. Please like, share and subscribe this video. Thank you guys.